So, like Delaney said, my name is Vimig Socrates, and today we're going to be answering the question, can we use computers to understand language? Well, it turns out, yes, you can. So we can all go home now. Just kidding. That's only sometimes true. So we're going to be talking about when it's true, when it's not true. Oh, hold on. Let me open up the chat and make sure there's not a, okay, cool. And why it's so hard for computers to understand language, even though we learn language when we're, kids 2 or 3 years old, and we get better and better at it as we grow up. Okay, so just a little bit about me beforehand, though. So I'm a fourth-year grad student in computational biology, and I work currently at the Yale New Haven Health Hospital Systems in the emergency department. I'm originally from India, but I moved here when I was like 3 or 4, and I moved to Chicago. So I'm a big believer that deep dish pizza is way better than any pizza y'all have here. And shortly after that, I went to Cleveland, a little bit east, and they always have pretty pictures that make it look like this. I studied computer science there for a few years, but usually it looks like this. There's just a single sad kid walking in the snow and all the trees are dead. And so I continue that trend, moving a little bit more east. And so now I'm in New Haven, working in the hospital system, and I'm in computational biology. And so that's our logo over here. Okay. So during this talk today, we're going to be answering 3 main questions. So what is language modeling? How does language modeling work? And what can we do with a language model? So the answer to the first question is pretty simple. A language model is just a really fancy word or a set of words for being able to predict the next word in a sentence. So, when you speak or when you use the internet, for example, Google do this all the time. So we're very familiar with this, and we as people are really, really good at this. Okay, all right, hang on. All right, maybe I should have picked slightly harder sentences. Yes, you're right. The first one is row, row, row your boat, and Mary had a little lamb. So that's really easy for us to do as people, but it's really, really hard for computers. And so we're going to talk about a couple of the reasons as to why it's so hard for computers to do this. So I just want to show you a couple examples. I'm sure you've seen a ton of those autocorrect fails. So here's one in the sentence, my dad barks too. We have to comfort him. And then, they make fun of this person for saying dad, but really their phone auto-completed to dad instead of dog. And the reason it does that is because maybe the phone thought that dad was a more likely sentence. So we'll talk about why that might happen. I'm not going to read this one out loud, but if you know this song, this is also a potential mistake in autocompletion that might happen. And so how can we try and get computers to do this better? That's kind of the question we're talking about today. Okay, so why is language so difficult? So I'm going to show you 2 sentences, and you all are going to put in the chat what you think to the answer to my question. So the first sentence, they're actually the same sentence, or mostly the same. So the sentence is, the cat sat on the mat because it was fat. So in this sentence, what do you all think the pronoun here refers to? Okay, Garfield, yes. Okay, yeah, exactly. So if you all remember from English class, it refers to the word cat. But what if we change the sentence just a little bit? So let's change the sentence, let's change the last word from fat to flat. So the cat sat on the mat because it was flat. So what does it refer to now? Yeah, exactly. So it refers to the word mat. And so all we did was change a single letter, and to a computer, that might not mean a lot, but because of how we understand the world, we know that cats cannot be flat, right? But mats can. And so we know that the pronoun is going to refer to the word mat instead of cat, and same in the first sentence. So we can use our knowledge about the world to understand these sentences in a way that computers can't. And these particular sentences are actually sentences that are used a lot to try and understand how good a computer is at understanding the world around it. And they're called Winograd schema sentences because they were made by this guy named Winograd, and they're particularly made to be confusing for computers. In general, these particular sentences, one of the main issues is that pronouns can be difficult to match to the words that they refer to, and these words, mat and cat, are usually called antecedents. And so what we need is this thing called context, which is our understanding of this world that computers don't necessarily have. And so I'm going to be talking about particular methods or tools that we use in my field that use and learn context. But before we can do that, we'll need to talk about this idea of probability. So if we want to answer the question, how do computers actually guess the next word? The answer to that question is they would use the probability of a particular word appearing in a sentence. So what is probability though? So the probability is basically just the chance of something happening. So let's say we flip a coin. What do you think the chance of getting a heads is? Yep, 50-50. Yeah, names went by way too quick, but somebody said 1 out of 2. So yeah, 50 out of 100, right? There's 2 different ways of doing it. So 1 out of 2 for the probability of getting a heads. And we represent the probability or the chance of something happening with the thing that we want to have happen. So the probability of getting a heads is 1/2. We can do the same thing with dice. What about the probability of getting a 4 on a 6-sided dice? Yep, 1/6, exactly. And so these are very simple examples of probability, but in the real world, probability doesn't just happen on its own, right? So we have a lot of things that happen that are related to other things. So for example, let's say it's raining outside and we are trying to decide whether or not to take an umbrella. So whether or not we take an umbrella outside depends on whether or not it's raining, not cloudy, raining, I guess maybe cloudy too. So in this context, the probability of us taking an umbrella outside, given that it's cloudy, is 3/4. Let's just say, it's just a random number. The point though is, let's say it's sunny outside, then the probability of taking an umbrella out, given that it's sunny, is much lower. So this idea is called conditional probability. And we'll use this idea a lot in sentences, because the words that we put in a particular order to make a sentence depend on the words behind it, right? So we have some conditions that happen. So I'll talk about this in the next couple slides here. So the key point here is that words aren't like dice. And so how do we calculate the probability of words in a particular order? Let's say, for example, we have this sentence. The sentence that we want to find the probability or the chance of occurring is, where are we going? And so the context, if you remember from before, the context is sort of the words around a particular word that we're trying to predict are the previous words in the sentence. So how do we get the probability of the sentence, and in particular of the word going, that we're trying to predict? So what we would do is we would create a probability of the first word. So the probability of the word where in, let's say, a bunch of different books that we look at. So we read a bunch of different books and we say that the word where shows up very often or not often, and we give it a number. And then we have to use that conditional probability. So we're also going to say, what is the probability of the word are, of the word where, of the word are given the word where? And so we ask that question as well, and we can multiply these 2 chances together. And if we keep going all the way down the sentence, eventually we can get the question, what is the probability of the word going given all of the other words in this sentence? And so we can multiply all these numbers, all these numbers together to try and get how likely is this particular sentence going to occur. And then, your phone can use those numbers to decide whether or not the word going is most likely when you type in the words, where are we? Or maybe it's, I don't know, tomato. So tomato is not going to be very likely. So it'll usually pick a word. And so sometimes these words are similar or not similar. And so that's why we have autocorrect issues like dad or dog, etc. Okay, so where do we actually get these probabilities from? So I'm going to talk about how a lot of the sort of tools that we're talking about in the next couple slides are going to use this giant data set. It's called the Common Crawl data set, and it's made of 145 terabytes of data. So that's like a very hard number to understand. But if you think of the hard drive in your computer, it's 300 of those hard drives. And our tools, our machine learning tools, which I'll describe in the next slide, read all of this text, and that's how they understand how likely words are to come in particular orders. And so what's actually in this data set? So we have around 100 million web pages. We have 8 million web pages from sites like Reddit and Tumblr, where people can upvote or downvote particular pages. We have millions of books and scientific papers, like the ones that the other exploring science speakers have talked about. And we have 6 million Wikipedia articles. And so we take all of this data together, and the model reads every single one of these documents and tries and predicts the next word in every single sentence. Okay, So what actual model do we talk about? And so just a little bit of background. The models that I'm going to be talking about here are based on this idea of machine learning, which is just a fancy term. I'm sure you've heard of it, but it's just a fancy term for trying to predict different things. In our case, we're trying to predict the next word in a sentence. And so there's a couple different models and they all have fun names, which is why Sesame Street and Transformers are coming to the rescue. We have one called Elmo. We have one called ULM Fit. It's just, people use the Cookie Monster because it's fun, but it has nothing to do with the Cookie Monster. And we have Transformers, but not the ones that you're normally thinking of. These are also machine learning models. We also have one called BERT, which is where the Sesame Street thing comes from. But in particular, we're going to look at this one made by this company called OpenAI. And we're going to open it up a little bit and we're going to look at what's inside. So this is a very complicated model that people have spent, I don't know, 5-6 years making, but we're going to talk about one particular component of it, which is the most important part. And these are called neural networks. So in order to describe a neural network, we're going to try to answer a pretty fun question. We're going to try to answer the question of, is this picture a cat? Okay, so let's say, for example, we have 3 people that are going to decide whether or not something is a cat. So these people are all going to be neurons in our neural network. Okay, they're the main component of the neural network, and they're the main sort of piece of the neural network. Okay, so if we put all of them together in a row, we'll call this one layer of the neural network. And we're going to have each person vote on whether or not they think that this is a cat. So this person here thinks on a scale of 1 out of 10, they think it's the chance of 4 that this is a cat. And this person thinks it's a chance of 2, etc. And so these numbers are called weights. So each neuron will have its own weight. Okay. And we can combine all of these together and we can add them and subtract them and multiply them together along these things called edges to decide whether or not this is a cat. So they'll all kind of work together and basically we'll take an average over these to figure out whether or not this is a cat. The issue though is when you have a single layer, a lot of times it's not complicated enough for us to decide based on every single picture that's out there whether or not something's a cat. So what we can do is we can add some more friends. And so we'll have another set of 4 more neurons and we'll make another layer of these neurons. So what's going to happen here is they're also all going to vote and they're going to tell their votes to the people in this first layer. So every single one of these people, all 4 of these people down here in layer 2 are going to talk to all 3 of these people in layer 1, which are where all these lines come from. And then, for example, this guy on the left here, this pirate, will use all of these numbers to decide, okay, I think that this person on the left is really trustworthy. And I don't like what this person's saying in the middle here. And so they'll decide which ones they trust more and they'll make a decision based on whether or not this is a cat. So this is how all 7 of these people work together to decide whether or not something is a cat. And the point of a neural network is to see a lot of these pictures over and over. We'll see hundreds or thousands or millions of these pictures. And eventually, all 7 of these people will learn whether or not something is a cat, and they'll all work together and do a good job. So what does that actually look like? Let's say, for example, we're given something that's not a cat. So we know this isn't a cat, but it's hard, again, for computers to understand these sorts of ideas. And so let's say, for example, we give it this picture of a dog, and we say that this isn't a cat. In that case, all of these people are going to have to change their votes to be closer to whether or not they think that this is a cat or not. So for example, this person in the bottom left really still thinks that this is a cat, but it's not. And we've told them it's not. So what they'll do is they'll change their number to be much lower. And so that's kind of how, if we keep doing this process over and over and over, eventually all of these people will have a good idea of whether or not something is a cat. Okay, so that's generally how neural networks work. Okay, so how does that apply to our task of trying to predict the next word? So we have the exact same thing here. Each of these circles is going to be a neuron. We have the input sentence. So we give the neural network a sentence. The students open there, and we're trying to predict what is going to be the next most likely word. So we still have edges, right? So we have multiple layers. We have layer 1 with all these neurons and layer 2 with all these neurons. We have edges between them. And instead of predicting whether or not something is a cat, what we're going to do here is we're going to take all of the words that we know about. So every word that we know from A to Z, and we'll try and figure out what is the likelihood of each of these words following this sentence. The students opened there. And if you remember from before, we read a ton of different books, right? Our neural network read millions of articles, web pages, textbooks, etc. And after reading all of those, it decides that we think that books is the most likely word to follow this set of sentences. So the students opened there, the most likely word to follow this list of 4 words is going to be the word books. And the second most likely is laptops. But for example, the word zoo is very, very unlikely because it's very rare that the model has ever seen, the neural network has ever seen a sentence that says the students opened their zoo. Although that would be cool to have a zoo. Okay. So that sort of explains a little bit about how these models work and how we train them and how we get them to understand language. The key component here to know is that they're really not understanding anything about the world, though. All they're doing is deciding whether or not words are near each other and understanding that, right? So what can we actually do with these models, though? So one of the things that we can do, so the transformer model that I was talking about earlier was made by Google, and they used it back in, I think, 2018. So if you remember, Google searches before that were terrible, and then they got a lot better. So here's an example of that. Let's say, for example, we type into Google, can you get medicine for someone pharmacy? So we obviously understand what that means, right? We're looking for whether or not you can pick up somebody's medication at the pharmacy. But before we use these new fancy transform models, the way that Google would answer this question is they would look for nouns. So they look for the word medicine and pharmacy, and they'd say that those are important words. So we're just going to give you results that have to do with getting prescriptions filled. However, now that we're using these fancy transform models, we can kind of understand the relationship between these different words. And so we can answer the question of, can somebody else get your medicine for you? And so that's the first answer that we get on Google now. And so we can see that it's gotten a lot better since before they used these new models. Here's another example of that happening. So I don't know if anyone in the audience reads Hindi. I do not, so I don't know what this says, but this is a sentence in Hindi. And so we can also improve translation. So in the old days, the translation that we would get is, here we have discovered with open eyes is no end to the adventures, which is like basically a nonsense statement, right? It doesn't really make any sense. And basically what they do is they took every word and they translated every single word in order. So a lot of times languages don't work like that, right? When you translate something, if any of you speak 2 languages, sometimes like one of the words means 2 words, or one of the words is in a different order than other words. So that happens a lot. And so understanding the relationship in translation is also really important. So now, if we translate this sentence using transformers, we can see that the outcome is, if we search with open eyes, then there is no end to adventure. So this is another example of where these models work really, really well, and they've made our lives a lot better. Okay, so a little bit of what are people currently working on with these models. So the first model came out around 2017, and people have been working on this for the next 5 or 6, 7 years. And so the biggest thing that they found is that as we increase the size of the model, so if you remember, we talked about a set of 7 neurons. The smallest model back in 2017 had 94 million neurons. So it's a very large number to comprehend, but the key here is that as we got bigger and bigger, our model ended up getting better. So the current model has 530 billion neurons, which, I'm pretty sure this is true, is still not equivalent to the number of neurons in our brain, I don't think, but it's getting close. Okay, so why do we keep making these models bigger and bigger, though? So we can see, don't worry about all of the words here, but basically, as we increase the number of neurons in our model, we can see that our results get better and better. So this is like how accurate our model is in question answering, and this is just a score that we give for how good of a summarization you can get given a particular set of text. So I'll show you examples of both of these in just a second. But the key here to note is that this line keeps going up as we add more and more neurons to our model. So we can tell that our model gets better and better. But that's not, that doesn't come with, we don't get all of that for free. So actually, people have done studies on how expensive is it to train these models. And actually, there's a study that came out recently on how much of an environmental impact does training these models cost. So these models run for weeks or months even to train. And so when we do that, let's say, for example, we're having, one of you is flying from New York to San Francisco. So this is measured in the amount of carbon dioxide pounds that's output. So it's around 2,000 pounds if you fly from New York to San Francisco in a plane. And training one of these models is around 200. And so if we train 10 of these models, which is usually done in order to figure out the right set of switches that you have to turn on and off to get them to work properly, it's the equivalent of flying all the way from New York to San Francisco. So as these models get bigger and bigger, it becomes more and more of an issue, both for how much it costs and for the environment. So this is something that people are currently working on. How can we make models that are smaller but still work just as well? Okay, so now I'm going to show you some of the more fun things that you can do with these models. Hang on one second. Oh, if I can close this, there we go. Okay, so I have a couple examples here for y'all. This is by that same company, OpenAI. I'm hoping everyone can still see this. I think they can. And so there's a lot of different things you can do. So this particular task that I'm going to show you is something I use a lot in my research, trying to figure out what doctors mean when they write text. But the point of this sentence, so this first sentence here is going to tell the model, what do we actually want from you? So we have a list of sentences, a list of companies, and the categories that these companies fall into, right? So we have the companies Apple, Facebook, and FedEx. And so if we ask the model, what kind of company is Apple, we can just hit submit, and we can see that it's a technology company. And we can do the same thing. So let's say we change this to FedEx. And remember, this is just based on the model reading hundreds or millions of different articles. Oh, sorry. Sometimes it doesn't work if you have a bunch of extra spaces, but and so based on reading all of those different articles, it determined that FedEx is a delivery company. But it's pretty easy to mess up. Let's say, for example, I don't know, we put in Lululemon. This may or may not work. I haven't tried this yet, so let's see what happens. Oops, sorry. I gotta get rid of all those spaces. Okay, so it finds out that it's a clothing company. So it's pretty cool. Just based on reading all these web pages, we can determine even companies that it hasn't seen before. It can figure out what kind of company they are. So that's super cool, but it's not very exciting. So there's a couple other cooler things that we can do. This one might be particularly relevant to you all. So we talk a lot about science here, and it's all graduate student research. And so let's say, for example, you get super curious and you open one of our papers and you want to see what it is, but it doesn't make a ton of sense to you. You could go to this model and you can say, can you please summarize this sentence or the set of sentences for a second grader or a third grader? And we can hit submit, and we can see that we have a much shorter sentence that is a lot clearer. We got rid of a lot of the different annotations for references, and we made the language a lot simpler. So the model can do some really cool things. I have tried this before and it didn't work, so let's see what happens. Let's say, for example, I know that you all are, middle schoolers. Let's say it's for a sixth grader. I'm not sure what'll happen. Let's find out. Okay. Okay. So it's slightly longer. I've looked at this a bunch of times. I'm not sure if you all got a chance to read it really, really quickly, but the sentence looks very similar though. So I'm not sure that it really worked in the way that we want. It's not that much more complicated than a second grader. So the model is very much based on the different kinds of things that we teach it to do. And so if it comes across something it hasn't seen before, it's going to be a lot harder for it to understand. And you'll see that when we do the breakout room activity in just a second. Okay. But this is one of my favorite ones, so I just want to show you one last one. I have a couple more examples, but this is one of my favorites. So we can convert movie titles into emojis. And so we're asking the model to do this, but then we give it a bunch of examples of what do we want it to look like. So if we give it the movie Back to the Future, then we have a young person and an old person, and they're in a car going back in time. If you've seen the movie, that's what it's about, I guess, in emojis. There's also a Batman, which is just a fancy guy and a bat. And so if we look up what that would be for Star Wars, we're going to get a couple stars and a spaceship, which is pretty cool. But we can also do, for example, let's say we do like Ready Player One, if anyone has seen that. And we'll get like a video game, and for some reason, this like weird hat thing. It used to show a person, so it changes depending on what the model is currently thinking. Okay, does somebody have one more movie for me to try, just because I like playing with this thing? Okay, that's a good one, because I don't know what's going to happen. it might just, oh, okay. So it just says up. So it really uses the, so for example, if we were to come up with that was a great example, actually. If we were to come up with a description in emojis of what the movie Up is, we might have balloons and we might have a house, right? Because we know what the movie Up is about. But for the model, it just sees the word up and it's like, oh, there's an emoji that's kind of like the word up. I'm just gonna put that in. Okay, I see a bunch of Jurassic Park / world. You guys are gonna make this real hard for me. I don't know how to spell Jurassic Park. Hold on, I'm just gonna copy it. I think one of you spelled it right. Is that right? Okay. All right. Okay, Jurassic Park. Oh, that one worked. Well, sort of. It has a dinosaur and I don't know, a fancy castle. Okay, I'll do one more. Let's see. I see Inside Out. I can do Inside Out. And I can send this link to you all. It does cost some money to do, but they give you like a little bit of money to play around with it. So I'll send the link at the end of the talk. Oh, this one's pretty cool, actually. So it has a heart and a braid. Nice. Okay, that was fun. All right. So, okay, one more example for you all. So in talking about what people are currently working on with these models, for example, one of the things like we've talked about a few times that people don't really understand, or that the model doesn't really understand, is things that happen in the real world. So for example, let's say, for example, you have this sentence, you're having a small dinner party and you want to serve dinner in the living room. But the dining room table is wider than the doorway. So in order to get it into the living room, what will we have to do, right? So we can think about like, oh, okay, maybe we'll have to, take off the legs, like turn it on its side and move it in, something like that. So right now we're using the most complicated model. So it's going to do a pretty good job, actually. Okay, that one was super boring. Usually it has like something more interesting. Let's see if we can get the same one. Something more interesting. There we go. So it'll like usually give you like a list of instructions, or it might like fill out the text in a different way. So this is actually OpenAI's most complicated model. And you can see that in this like little circle here. So it was trained on the most amount of data. And they even say like it's good at things like cause and effect and creative generation, those kinds of things. But if you remember, the smaller the model, the less text it's read and the less it understands. So let's say, for example, we took the smallest model and we try and get it to predict something. And so it says, if you want to try to get the dining room through the doorway, you will have to use a screen. You can use this design to get a dinner party, blah, 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 without having a kitchen stove. And it just kind of makes stuff up. It has nothing to do with getting the living room table into the dining room table into the living room. And so we can really see that the more text that it's read, kind of like us as people, right? The more text that we read, the more we understand. But this is especially true for these neural networks. Okay, and there's a ton of other examples of this. I can maybe drop this in the chat and you all can look at it, but there's a lot of really cool examples of this. For example, in this sentence here, we poured ourselves a glass of cranberry juice and we also accidentally added a teaspoon of grape juice. It seems okay, and you try smelling it, but you have a cold, so you can't smell it. So what do? And so in the bold is what it actually is what the model predicted for the next word. And so it says you drink it and then you die. So that doesn't really make sense, right? So some of these simpler models can even be dangerous if they aren't learned properly based on the text that they have seen. Okay, so those are all the examples I have for you all. So now you're going to get a chance to play a game. If you've ever played Oregon Trail, it's kind of like that. It's basically a text-based game. So all of the volunteers have this link. They're going to go on there. I'll just show you quickly what it's like. So basically, you would go on here and 1 second. You would start the game and you can pick from a bunch of different settings. So pick whichever one you like. Let's say, for example, we do fantasy. And you get to pick what kind of character you are. And you get to give it a name. Let's say his name is Henry. And you'll see, so right now the model is coming up with a bunch of text based on the things that we gave it. And you're going to interact with this model and you'll try a couple different things. So you'll play the game normally, and then you'll see if you can break the model and then what happens when you break the model. So hope you all enjoy it. And yeah, thanks for listening to my talk.
Hey, Vimig, I'm here to ask you some questions. That was really fun in my breakout room. We had a lot of interesting stories. Some people were being chased by a madman. We had some detectives and spies, and it was crazy. But yeah, thanks for showing us that. And so I collected some questions that we've gotten over the course of the presentation. One question I actually got in my breakout room was about like the AI and everything. Are those things free? Like who pays for these things? How does that work?
Yeah, that's a really, really good question. It's actually a big, it's a hot topic because OpenAI in particular, the models that we looked at and the website that I showed you, they used to be free. And their most recent up-to-date model, they sold exclusive rights just to Microsoft. So everyone was all up in arms about it because they were like, oh, no one else can use it except Microsoft. And so it's a difficult problem because they cost millions of dollars to train. And so somebody has to pay for them. Usually it's a big company like Google or something like that. What they'll do is they will release the data set and they'll release what the model looks like. All of those like specific parts of the neural network they'll release, but they won't release the fully trained model to the public. And so that's one way that if you had the money, you could train your own if you wanted to.
But we could play with it for free, so that's fun.
Yes, exactly.
Another question that we got earlier in the program was, does this technology also work with voice assistants? Is that like kind of a similar thing, like learning people's voices?
Oh, I see. That's a good question. It's similar but pretty different. So there's basically just one earlier step that you would have to do. You would have to convert like the voices, so the sounds that you would hear. If you've ever seen on Spotify, like you see like the spectrogram where like the lines move up and down. So if you've ever seen that, you have to convert that into words, and then everything after that is the same. So you do that first piece, and that is like a whole separate ball game. It's just as hard, and a bunch of other really smart people work on it. I don't know anything about that, but if you're interested in it, you can look up like audio signal processing or some of those sort of keywords, and that will help to learn more about it.
Okay, and one last quick question before we end the session. Someone just asked in the chat, if you had to guess, how many endings are possible for one character in the game we just played?
Oh, I have no idea. I
A
mean,
billion, a trillion?
I would say in the millions, high tens of thousands to millions, only because I think it's not completely freeform. So they like coded a couple of things to like kind of make it like a reasonable story. So they've like kind of made the model go in a particular direction. So it's not as completely like freeform as it normally would be. If you just let the model go, it would make millions or billions of different guesses. But most of them wouldn't make any sense. So.
Well, even with tens of thousands of options, I'm sure it'll give us lots of time to really explore
Yeah.
and have a lot of fun with it. So thank you again, Vimig, for giving us tens of thousands of opportunities of fun and getting to learn about how this process even works. I'm sure I had a lot of fun today, and I'm sure everyone else did as well. Yeah, thank you so much for sharing your work.
Yeah, thank you all for listening. That was a lot of fun.